Good morning, chemists and other scientists. Welcome back to Chemistry 132b, Quantum Principles. This is lecture number 2. And in lecture number 1, we introduced the concept of quantization of the energy of photons and also the energy of electrons. We talked a little bit about the fact that electrons have wave-like properties, and in general, particles at small scales could, in principle, display quantum mechanical wave-like behavior. So I'm going to start with this question right here. It's not so hard, but I'm going to just do it anyway. So I'm going to launch the poll and allow you to select the right one. Shouldn't be too hard. Just as a warm-up. All right, people are going at it. At light speed. Okay, I'm going to stop it already. Most people have already answered. The right answer is electrons. Okay, and the reason why I'm asking this question is just to make sure that people are appreciating that quantum mechanical effects really are effects that are relevant on small scales for particles that are very light. Okay, so electrons, they do have those properties because they have a mass that is very, very low. Okay, and if they are confined in space, such as is the case as when they are a part of an atom. Okay, so when they're bound to an atom, so when the electron is part of an atom, then it is very confined in its mobility or where it can go. And those are situations when quantum mechanical behavior can be seen. Tennis balls are too heavy to have this property, and so the wave-like behavior of tennis balls will not be manifest. I mean, you can calculate what the wavelength is, but it will be so small that it becomes really very much irrelevant. Red blood cells is the same story. They're much smaller than tennis balls, but their weight, of course, is much, much higher than that of electrons, and so their wavelengths also are insignificant. Interstellar dust sounds very interesting, but again, the same kind of reasoning can be applied here. Still too heavy to display meaningful quantum mechanical wave-like behavior. A silver bullet can travel really fast, but not nearly as fast enough to have any significant quantum mechanical behavior because its mass is way too high. So all of these B, C, D, and E are not displaying any meaningful wave-like behavior in the quantum mechanical sense. The electron is the only particle here that has meaningful quantum mechanical behavior. Okay, so just to kind of rephrase some of these things that we talked about in lecture 1, quantum mechanical behavior is evident on small spatial scales, okay? And this is the case for atoms. Atoms are very small, okay? They occupy a very small portion of space, and as we know, they are composed of a nucleus with electrons around it. Those electrons, therefore, are confined to a very small spatial scale, okay? And the combination of their wave-like properties, the wave-like properties of the electrons, and the fact that they are confined in a very small segment of space, that leads to quantization of energy. And we will see that. We will see that come out, okay? If that is not clear to you from this sentence, then you don't have to worry at all, because we will exactly point out where this emerges, okay? In what situations this comes to the foreground. Now, just to kind of restate something I said last time, if electrons would not have wave-like properties, okay, then atoms could be described classically, and they would have very different properties. Okay, so the very fact that electrons have meaningful wave-like properties, that is the reason why atoms have the properties that they do. If this was not the case, then everything would be different, okay? So this is a very important fact. The wave-like properties of electrons is the reason why the atoms have the the quantized energy states that they have. Okay, so let's now jump into a little bit more of I would say, mathematical framework. Okay, we have to do this because some of it is needed to appreciate the effects, the quantum mechanical effects that we will be considering in this course. So we are talking about electrons. Our goal is to describe how electrons organize themselves when they are part of an atom. Okay, that is the goal. Okay, and we have concluded now so far that electrons have wave-like properties, they have quantum mechanical behavior. And so what does it mean? We have to, at some point, arrive at the description of the electron. And so the way that happens is through a wave function. I know for sure you have heard about wave functions. And the wave function of an electron in an atom is typically indicated as follows. It is the letter psi, the Greek letter psi, and then it has subscripts, those are indices, and those are the quantum numbers that fully characterize the state of the electron. N is the principal quantum number, L, the angular momentum quantum number, ML is the magnetic moment quantum number, and MS is the magnetic moment that is there because of spin, the electron spin. So this total of 4 quantum numbers fully characterizes the state in which the electron sits. And that is indicated by psi. So psi is called a wave function. And the wave function, the best way to kind of like describe what the wave function does is it provides the state of the electron, the state the electron is in. It is a full description of the electron. Okay, so the wave function contains all the information there is to know about the electron, the state in which the electron sits. So you would think, okay, fine, let's calculate this function and move on. But it turns out, in order to calculate this function, we need a different mathematical framework than the framework we use in classical mechanics. And secondly, if we would like to use this function to learn something about the electron, for instance, where is it, how fast does it move, and what is its exact energy at this particular moment, then the function itself doesn't give a direct answer. It describes the state, but it doesn't describe the observable, the things that we can actually observe about the electron. And so this is really confusing at first for most people. And so we have to talk about how do we work with wave functions and what are the properties of these wave functions. So that's what we're going to try to do today. We're going to make a start with kind of like diving into the world of wave functions. Okay, so let's see if I can pop up the whiteboard. Here it is. So in classical mechanics, we typically work with functions. Let's say a function f, x, and t describes the whereabouts, that is the position x, and at each time t of a particular particle. Let's say we have a particle that can be described classically, then this function x and t, f with variables x and t, basically gives me the location of the particle at any time. And if I know the location at any time, I can also calculate the velocity, I can calculate the energy. There's basically everything that there is to know about the particle is something I can figure out using this function. And this is typically what we learn in classical mechanics in physics courses. Now we have something that looks like, let's say, this. Okay, this is the psi, also x and t. But even though this psi has the x in it, that's the position in space, and this is the time at which we are considering the situation, this function doesn't immediately give me the whereabouts of the electron. That's very confusing. And because of that, I can also not just immediately know where the electron sits, or what its energy exactly is, or how fast it moves. Okay, so even though the psi gives a complete description, it doesn't give me the direct observables that I'm interested in. So how to think about this? This is a little bit confusing, so I'm going to just schematically draw this. Hopefully this will be clear. So here is the function. This is the wave function. And it contains everything there is to know about this particle. And in this case, it's the electron. Okay, so this is just a circle around it that basically indicates it describes everything there is to know in the space in which the electron sits. But I'm interested in particular things. Let's say, where is the electron? Okay, And so in order to know something about where the electron sits, I have to do something to this wave function to get the information out. Okay, so I have to kind of, in this case, operate on this wave function. This is an arrow, sorry. Okay, with an operator, and the operator is, let's say, the position operator. Okay, so an operator typically is indicated by this symbol, and this symbol, this operator, does something to this function, and as a consequence, after it operates on this state function, I get an answer. Okay, so let's say if I have this operator and I operate on this wave function, I get something out, and what I'm getting out is related to the observable that I'm interested in. So if I'm operating on this function with a position operator, then the answer has to do with the position of the electron. If this operator is a momentum operator and it operates on the wave function, then the answer that I'm getting has something to do with the momentum of the electron. And the same for energy. If this is the energy operator, then this operation here will tell me something about the energy of the particle. Okay, so this is really different from the function f of x and t in classical mechanics, because it tells me immediately the whereabouts of the particle, the speed of the particle, and the energy of the particle. Right? So it's different. And this is confusing at first, but we will see that it's actually, even though it's different, it's still a framework that we can work with. And after a while, you will come to appreciate and hopefully become fluent in it. Okay, so we have to talk about two things here. The first thing is this operator thing, like that. What is it? And then we have to learn a lot about the wave function itself. And so the next couple of lectures, we'll be devoting our time on figuring some aspects out about the operator and the wave function. Okay, so I'm going to start with some of it. It's not complete, but I'm going to have to start somewhere. So we're going to dive into what the wave functions and the operators do. Okay, so let's start with, let's say, defining just an operator, because that seems like a little bit mystical. What is it? So let's just write a particular function. I'm just going to do f of x, okay, to make things simple. What if an operator operates on a function? What happens? Give me an example. Well, let's take this to be a very simple operator. Let's say the operator is simply, okay, a constant, c. Okay, then this operation will give me c times fx. Okay, very simple. So the only thing the operator does is multiplying the function by a constant c. All right. Well, let's say I have a different operator. Let's say this is x. That looks a little different, because now this operation will yield me something very different, which is the operation of this operator onto a particular function will give me x times fx. So this is not a constant, of course. This changes the overall function quite a bit. Okay, but that's what this operator does. So let's look at yet another one. Okay, because an operator can be anything. Let's say I take the derivative. Okay, so that means that the operation on a particular function will now be taking the derivative of that function. All right. So what does that mean? Well, that means just, taking a derivative. So let's look at an example like this. So let's say fx equals an arbitrary function. Let's say 2x squared. Okay, so let's do that. I can calculate quite easily the derivative of that. I simply take a derivative of 2x squared. And most people can do that, hopefully. Answer is 4x. Okay, done. So that is when the operator taking the derivative of operates on the function 2x squared. I get 4x. That's it. End of story. Now, let's do the same thing for a different function, where the function is not 2x, but the function is actually an exponential function. So let's say I'm taking a new fx. In this case, the function is an exponential function. Okay, e to the power ax. Okay, so I'm going to do the same thing of this function. taking a derivative of this exponential function. There it is. And most people can do it. That's simply a times e ax. All right? Looks pretty good. It's a little different from the 4x, because in this case, what I have this, which is the function fx. Okay? So this operation I can actually write like the operator is operating on the function, and what I'm getting is some sort of a constant. Okay, let's call this constant just omega times fx. Okay, so an exponential function with a constant a that I now write as omega. That's basically the same. Okay, but this makes it more general. So operator is operating on a function, and what I get is a constant times the function again. Okay, so this is a very interesting situation, and it's so interesting, in fact, that it has a specific name. Okay, this is called an eigenvalue equation. What does that mean? Okay, well, let's make sure that we summarize that properly. So we're dealing with a situation where I have an operator operating on a function, and what happens is there's a constant times the function again. Okay, that's the situation I'm dealing with. So I'm going to give these things names. This is the operator. Operator fx is now called the eigenfunction. Eigenfunction. Ooh. I'm still getting used to this writing pad, which has a very interesting response. It goes way out of bounds all the time. And then this omega, which is called the eigenvalue. Eigenvalue. Okay, so those are the names that we have. Maybe you've seen this before in your math class, and if you have, and that's great, because we will use it actually quite extensively in this course. So this is an important situation. Now, let's look at another operator. Let's say dx squared. Okay, so this is my new operator. And I'm going to ask myself now, for which functions fx can I choose such that this condition here is fulfilled? Okay, so which function will make sure that if it is operated on by this particular omega, okay, taking the second order derivative, will give me the function back times a constant. Okay, so maybe you know a function that has this property. For instance, if fx equals sine of x, okay, if you take the derivative once, you get, of course, cosine, and then you take a derivative one more time, you get the sine back with a negative sign. Okay, so in this case, what I'm having is, operating on x is the second order derivative of sine is going to give me minus sine x, right? So what this is basically a value which is now -1 times the function x, right? F of x. So this fulfills this eigenvalue equation. So I can now find more functions, perhaps, that also have that same property. For instance, cosine of x has the same property. It would also give the function back times a constant, right? So there's a whole bunch of functions that have this, that meet this condition. And so I can now write something more general. I can write that if I have a function n, okay, so f with an index n, that produces an eigenvalue, which now also has an index n, okay, then these n's basically are kind of the labels that label all the functions that have this property for this particular operator. Let's say this operator right here, okay, second order derivative. So this set of functions, f with the label n, is the entire set of all the functions that are eigenfunctions of this operator, okay? Now, why am I saying this? Because this is an important concept in quantum mechanics. This Fn is called a complete set. a complete set. It is the set of all the functions that are eigenfunctions of, in this case, this operator. But I could also consider this for a different operator. So it's a general concept. Give me an operator, okay, and once I have it, I'm going to try to determine all the functions that are eigenfunctions of that operator. And the set of those functions is forming a complete set. Okay, a complete set. So try to keep this in mind. So what I'm trying to show you now next is some very general properties of complete sets of eigenfunctions. Okay? So let's go back here. Can you guys see my wave function again? Yeah? Okay, great. Yeah. Okay, so here is something that seems unrelated, but you will see that I'm going to tie it together with what we're talking about here, which is a complete set of eigenfunctions. So here is the Cartesian coordinate system, and I'm choosing a point P. And of course, P is a function of x, y, and z. X is the distance along the x-axis, y, the distance along the y-axis, and z, the distance along the z-axis. So nothing special here, okay? So I can basically write the location of P as, and this is important, a distance x along the direction x. And that is indicated by EX, all right? Then the distance y along the axis, the direction of the axis of y, and then the distance z in the direction of z, which is E with a little hat z. Okay, so these are basically the unit vectors of the Cartesian coordinate system. And as you know, they are what we call orthogonal. What does that mean? That means that the vector product of EX times EX equals 1, okay, because it's a unit vector, and that if you multiply it, that's the vector product of it with another direction, then you get 0, because it's orthogonal. You can actually see it. It is orthogonal. Everybody understands that. But this has a name. This is called orthonormality, okay? Orthonormality. The word ortho, the part ortho, says that it is orthogonal. So the vectors here are orthogonal. And the normality means that if you multiply it by itself, you get 1, because it's a unit vector. So the whole thing is therefore called orthonormality. Keep this word in mind, because this will come back to us, okay? Now, these Cartesian coordinates, therefore, are 3 vectors. They are orthonormal, and I can say that they form a complete set. They are a complete set, meaning that every point in space can be expressed in terms of these vectors, okay? Namely, x times a vector EX, y times a vector EY, and z times the vector EZ gives me where the point sits, okay? So these vectors, x, y, and z, or EX, EY, and EZ, are a complete set of directions. There are no other. This is it. In Cartesian coordinates, that's it. It's a complete set. And they are orthonormal. Okay, so now we're going to make a kind of a leap of faith by doing the same thing, but not for unit vectors that represent the Cartesian coordinate system, but by, let's say, a coordinate system that has functions, okay, on the axis. So it's not a unit vector. It's now a vector that is actually a function. And I call it G, H, and F. All right? But that's it. That's the only leap of faith you have to make in your mind, because the mathematics is the same. Okay, so let's say a point in space, or a function in space in this case, is x times the character of y, y times the character of, x times the character of f, y times the character of h, and z times the character of g. Okay, it's the same thing. So this function that I'm describing has a little bit of f, a little bit of h, and a little bit of g, right? How much of each? Well, that's given by x, y, and z. So it is a point in function space, right? Where P now is a function, and I can fully describe this function in terms of f, h, and g, where f, h, and g are a complete set, meaning that if you could do a vector product of this function, then you would get 1 if it is f times f. And if you would multiply it with another one, okay, another function instead, you would get 0 because it is orthonormal. So this complete set of functions is orthonormal, just like the Cartesian set of directions is orthonormal. Okay, the conclusion is pretty much the same. In the first case, I could describe any point in 3D space in terms of its projections along the Cartesian axis, right? Here, I can describe any function as its projection along the complete set f, h, and g. That's it. Mathematically, there's almost no distinction. It's the same thing. Conceptually, this is hard to do if you see this for the first time. So why are we doing this? Because we need it, okay? This is part and parcel of quantum mechanics. So what we have is f of n, where n now is the label. Remember, it's like the label of the functions that fulfill the eigenvalue equation that gives me a full set. So if I exhaust n, I've exhausted all possible eigenfunctions, and therefore I have the complete set in my hands, right? These are functions, and we can think of these functions as representing a quote-unquote coordinate. Okay, so they describe what we think of, let's say, in Cartesian coordinates as a coordinate. Of course, now it's a coordinate that is an actual function. Okay, now, but they have the same properties as real coordinates in the sense that they are orthonormal, meaning that if I multiply function n with function m, and this is a vector type product, I will say something about that, because so this is a little bit symbolic, this dot here. What does it mean, this multiplication? I'll say a few words about that. But n times m is delta n m. What does the delta mean? The delta is called the Kronecker delta, and it is very simple. It is simply 1 if n is equal to m. So if the n and m are the same, then it's 1. If it's not the same, it's 0. Okay, so this is a very kind of concise way to summarize this product of two functions. If they are the same, if n and m are the same, then it's 1. If they are not the same, it's 0. In other words, these functions form a orthonormal set. Okay, just the same that we have been talking about for the last 5 minutes. And so, therefore, a function p along some kind of, as a function of a particular variable s, can now be expressed as a sum, a weighted sum of the eigenfunctions fn. Okay, where fn is a complete set, and I just have to find the projections of p along each of these coordinates, which are now functions, right? This is the same as describing a point in space, but now I describe a function in terms of an eigenfunction set. Okay, so this is a function, and this is the complete set. And I can express this function, any function for that matter, any function can be expressed in terms of a weighted sum of a complete set of eigenfunctions. Okay. Now, what does that mean? Well, let's go back to the whiteboard. And we can now state the following. Let's say I have a function, like any function g, any arbitrary function, can now be expressed as the same thing, as a sum over n with weighing factors Cn of a complete set Fn. Okay? So any function, no restrictions, any function can be described in terms of a weighted sum of a complete set of eigenfunctions. That's what we have been saying all the time now. I'm saying it in different ways, but it's the same thing, right? So we'll see this many times over, okay? So don't be afraid when you see this, because we'll be using this quite a bit. Okay, now let me ask you then, if I have an operator, any operator, okay? And the operator has as its eigenfunctions the set Fn, okay? So Fn are all the eigenfunctions of this operator omega. But this operator now is not operating on the individual eigenfunctions, it's operating on an arbitrary function g. Okay, so what is that? Well, let's write it out. Okay, so the operator, I know what g is. I'm going to express g in terms of the functions Fn. Okay, now that is interesting because what I can do then, I can operate not on, Cn, because that doesn't do anything, that's just a constant, but this thing can operate on its individual eigenfunctions Fn. And if it does that, I get an answer because I get Cn omega n Fn, okay? So if I operate on the function g, I get this sum of eigenvalues times the eigenset Fn. And this is something also we will see many times over in this course. We will use it in several occasions. All right, so this is one aspect, okay? This has to do with sets of eigenfunctions. So the whole concept of, oops, wow, that's bad. Sets of eigenfunctions. Okay. All right. Now, one aspect of the set of eigenfunctions is that the functions in the set are orthonormal. And this is very, very important. Okay. And so what I'm going to do then is kind of be a little bit more specific on how this is defined. So what I'm going to define is S. And S is the overlap integral. And so if I have an overlap integral, that's an integral sign, Fn times Fn star, where the star means complex conjugate. And if you don't know what it is, we'll get to it. Okay, it's a complex conjugate of Fm. Okay, the complex conjugate of Fm, dv, where v is simply integrating over the entirety of space of the relevant variable, and that is 0 if n and m are not the same. Okay, so actually I should maybe write it differently. How do I do that? Erase it. There. Maybe I should write this. Oops. Kronecker delta and m. Okay, so for a complete set, this holds. So I'm a little bit more specific now. Previously, I simply wrote a kind of a vector product, but that's kind of not the right way to do it. Okay, what we really have to do is the following. It's an overlap integral where f is multiplied with fm, complex conjugate, and then I'm integrating over all possible variables, dv. Okay, and so it basically says that if in the entirety of space this product is 0, then these two functions are orthogonal, n and m. If n and m are the same, then it's 1. So I have basically two situations when of this complete set, f and fm and fn are not the same, okay, then I get 0. So this is true when m is not equal to m. That means that these two functions, n and m, are orthogonal. Vice versa, if I have fn times the complex conjugate of fn integrated over all space, I get 1, okay, because n is now equal to n, right? So that means it is normalized with itself. So this is the condition for a orthonormal set of eigenfunctions. They have these properties. The overlap integral is 0 when n is not the same as m, when I have two different functions. It is 1 when I multiply the function with itself, with its own complex conjugate. Okay? All right. So let's do the following. Let's do an example. Okay, let's take a function. The function f of x is now e to the power minus ax. Okay, and this function is defined, let's say, in the interval x0 to infinity. Okay, so that's the interval I'm considering. And I'm going to ask myself now, is this function normalized over this interval? What does that mean? Well, that means that the integral fx star over the variable x, because it's a function of x, over the relevant interval, which is from 0 to infinity, must be 1. Right? If that's the case, then this is a normalized function. That's the definition. So it has to do with the properties of an orthonormal set. Okay, so I can summarize this as follows. This integral can be written as fx squared. Okay, this must be 1. So if that condition is fulfilled, then this function here is what we call normalized over this relevant interval. So we can do that. We can calculate this overlap integral, or this, in this case, not really an overlap, it's overlap with itself. So let's do that. Let's just write this out.
Worm.
That is the following.
Maker around 8 o'clock. Un verre, vers, vers, sans verre, vers un verrier, vers 20 heures.
Is somebody talking, folks? I can hear somebody talk in the background. Make sure that if you talk, you can mute yourself so nobody can hear you. Unless you have a question, of course. Everybody is allowed to ask a question. So I'm just going to write out this integral. The complex conjugate, okay, so the complex conjugate of this function is the same as the original function because it does not have a complex number in it. Okay, so this is what I get. This is the integral I have to evaluate. So that is, if I write it neatly, minus 2a x dx. Hopefully you can do this integral. It's an exponential function, so I can determine the antiderivative, which is minus 2a function itself. Okay. And fill in the values 0 and infinity, and that will give me the following. 1 over 2a.
Okay, but that's not enough of course. We take off the E. Oh, we change it up a little bit. We add some letters.
I can still hear somebody in the background.
What is this?
Can you please turn off your microphone, folks?
That thing there, huh?
Oh, they're not listening. Okay.
So much. Thank you.
Professor, I think you can mute them if you go into
maybe
the
I should.
name.
Let me see. Maybe that helps. Okay, so this is what I do. I fill in the values infinity and 0. Infinity is going to give me a value 0 here. That is going to give me the value 1. And so the answer to this integral is 1 over 2a. Okay. Oops. Apologies for this. I mean, I have such a hard time with this pad. Again, this looks nothing like my handwriting. It's completely stretched. Okay, so this is the answer to the integral. It's definitely not 1. Okay, it's not 1. So this function is not normalized. It's not part of an orthonormal set. So can I normalize this function? Can I make a change to this function such that it fulfills this condition here, this condition right there? Okay, well, I can do that. I can rewrite the function. I can say fx equals some kind of constant n, normalization constant, times the function itself. And if I find this n such that the condition for normality is met, for normalization is met, then the function should be normalized. So how do I do that? Well, I do the same thing. I'm going to have this condition, f of x dx must be 1. And what I have now, I have this now as my function. So it's going to be n squared. And then the same integral, okay, which is going to be minus 2ax dx with the same integration, limits, and I know the answer because I just calculated this integral, and that was, oh my goodness, 1 over 2a, right? That's what I just calculated. And so the integral is still the same thing, hasn't changed. And so this thing must be 1. Okay, so that's easy. That simply means that n squared equals, the 2a goes to the other end of the equation, to the right-hand side. N squared is 2a. That means that n equals the square root of that. Okay, so that implies, in the end, that my function f of x equals the normalization constant, which is now 2a square root times this function again is now normalized. So this is now normalized, whereas before it was not. Okay, so
Professor,
that's it. Yeah, go ahead.
I have a quick question. When we take the square root, it doesn't have to be plus or minus. Why is it that we choose the positive?
You are absolutely correct. That could be a negative as well. But you know, it doesn't matter because the answer is going to be the same. The condition is fulfilled, and we choose the positive value because that value is just easier to visualize. But yeah, in principle, you are correct. You can choose the negative value as well.
Oh, okay. I was just wondering. Thank you.
Mathematically, it's the condition is still fulfilled.
Thank you.
Okay, so that concludes basically the information that I have that I wanted to share with you today. Introducing the concept of eigenvalues, eigenfunctions, and the idea of a complete set. Okay, and the idea that I can express any function in terms of a weighted sum over a complete set of eigenfunctions. Okay, that's something that we concluded. And then finally, the property of complete sets is that they are orthonormal. And if they are not normalized, then we can normalize each of them in a way quite similar to what we have done here. Okay, so in principle, like if I give you a function and I say normalize this function, then this is the way to do it. Find the normalization constant n. So any question that says normalize this function means that you find the normalization constant n in this fashion. Now remember, you can have a very different function and you could also have different integration limits, okay? But that doesn't change the general recipe. The general recipe stays the same. Okay. All right, so next time we'll be diving into some properties about the operators. So this was about the wave functions, and we will be looking at operators a little bit more carefully. There's some interesting properties that they have. That is for Friday. Also, please attend the discussion sections because they will be very useful to ask questions about some underlying math. Okay, I know that Yinting has done a great job explaining some of the basic math formalisms that we will be using. And as well, we have a worksheet for you to think about. And also, don't forget that at the end of the week, we have homework. Okay, so those are 4 questions. In principle, they're pretty short, but you know, I want you to do those questions diligently and just think about what it means and you know how to solve those problems. All right, so that's due on Sunday night. So you can already have a look at them, but make sure that you complete them before the deadline on Sunday night.
Professor,